Hello again. Welcome to another lecture for Civil Engineering 547, Groundwater Modeling, Brigham Young University. I am Norm Jones, and today we are going to talk about hydraulic head concepts. Hydraulic head, sometimes we call it piezometric head. This is one of the most important underlying physical principles associated with groundwater modeling. It forms the basis of Darcy's law, which we'll talk about in our next class, and also both of which are then the primary components of the governing equation we use to solve groundwater flow systems using a numerical model. And hydraulic head is a principle that's taught in physics, and also if you've ever had a course on fluid mechanics, if you've taken the official prerequisites for this class, you would have taken fluid mechanics prior to soil mechanics, and in fluid mechanics you learned about hydraulic head principles, and in soil mechanics you learned about Darcy's law, which we'll talk about next time. Some of you may not have seen these recently, so you might want to go review other materials, but we'll give you a good review. We're going to rederive the primary equation associated with this, and then discuss a few examples to illustrate what it means. And then, of course, in class, we'll do some exercises associated with this. So, what is hydraulic head? Before we get to that, we want to review a concept called pore pressure, or pore water pressure. And that is when you have saturated soil or rock where the water fills up the pore space in the soil or rock. The pressure of the water in those pores we call pore pressure. And so I have a diagram here showing a saturated section of soil shown in blue. And above that we have an unsaturated section. And we're going to look at point A. And if point A is at a distance of H2, excuse me, let me back up a little bit. So the water, the line there, this little symbol right here, that's an indicator we typically use to represent what we call the water table. And that is, if you were to drill a hole in the ground, it's the level to which water would rise in a pipe. It's the top of the saturation. Now, in practice, the actual saturated portion of the soil could theoretically be higher than this because of something called capillary action. If you have really small voids in the soil, if it's a fine-grained soil, sometimes the capillary pressures in the soil, which you may remember from chemistry, would pull the water up above the water table. But that's a detail that won't really impact any of our work this semester, so I don't want to dwell too much on that. The main point is the water, that we will routinely use that little inverted triangle symbol to delineate the water table in our drawings this semester. So point A is or the water table is a depth of H1. Point A is at a depth of H2 below the water table. The pore water pressure is equal to that distance H2 times the unit weight of water. To get that, the unit weight, as you may recall, is equal to gravity times the density. But the unit weight is the more useful term when we're dealing with groundwater systems. It represents force per volume. And so in English units, it would be 62.4 pounds per cubic foot. In metric units, 9.81 kilonewtons per cubic meter. And so taken together, we have, if you multiply the height of the water times the unit weight, that the height of water is in length units, and unit weight is in force per length cubed. So you end up with units of force per length squared, which are the correct units for pressure. So in English units, it would be pounds per square foot, and in metric units, it would be kilonewtons per meter squared, or pascals. Okay, so that, again, the simple thing to remember here is the pore pressure at a point is the height above the point that water would rise if you were to insert a piezometer, or the distance from that point to the top of the water table, multiplied by the unit weight of water. Okay? So we'll come back to that and use that as we go through our lecture. So let's see. Let me go to the next slide. So let's look at this particular example. We have a column of soil. Suppose you had like a pipe in the laboratory, filled it with soil. And then on top of that, at point A, we have what we call a standpipe attached to that, and we fill that with water up to a distance of x. And then down at the bottom, we have another pipe where water is filled up to a height of x above point B. So there's water continuously through this pipe. In other words, the water rises above point A and point B to the same level. And therefore, since the pore pressure is the height of water above the point times the unit weight of water, we know that the pore pressure at point A is x times the unit weight of water. The pore pressure at point B is x times the unit weight of water. Therefore, the pore pressure at A is equal to the pore pressure at B. And A, the elevation of A, which we'll designate with ZA, is higher, is above or greater than the elevation of point B. So the question is, does water flow from point A to point B through the soil? Now the pressure at both point A and B is the same. So if the pressure is the same, why would water flow from point A to point B? That's, an interesting question. Is the flow of water through porous media, is it solely dependent on pore pressure? I don't know. We'll come back and later in the lecture and revisit this example. Here's another one. In this case, we've taken our column of soil and we've laid it down on its side. And now in this case, there's a standpipe above point A that rises to a level higher than the water level in the standpipe above point B. So therefore, the pore pressure at A is greater than the pore pressure at B. And to make things interesting, in this case, the elevation of A is equal to the elevation of B. So again, does water flow through the soil from point A to point B? If we were live in class, we'd do a poll. In my experience, sometimes people will vote no on this and yes on this. It's kind of intuitive to think that water flows from high pressure to low pressure, right? So it's a little easier to say water flows from point A to B on example 2. Example 1, pressures are the same. Would water flow? That's an interesting question. So we'll come back to that. And in order to solve this, we are going to look at something called Bernoulli's equation. Again, hopefully this is a review for you. It may have been a while since you've seen Bernoulli's equation. But we are going to rederive Bernoulli's equation. And the way we do that is we look at 2 points, A and B. In this case, we're thinking of points inside saturated soil. But and they are separated by a distance z. So in this case, Z denotes the distance vertically between point A and point B. And the question is, what work is done in moving a unit mass of fluid from point A to point B? What do we mean by a unit mass? That would be 1 kilogram of mass. In English units, 1 pound or 1 slug, I guess, depending on how you want to denote that, from point A to point B. So there are different components of that work that's required to move the mass. Part 1, let's just look at the work done in lifting the mass. How much force is it going to require? And as you may recall from physics, work is defined as force times distance. In this case, the force that would be required to move it from A to B would be the weight of the water, of the mass. And that weight is defined as mass times gravity. And we said it's a unit mass, so we're going to replace that M term with a 1. And we end up with G times Z. Again, G is gravity, and Z is the separation distance between the two. Next, we are going to look at the kinetic energy. And kinetic energy means that there may be, if the mass is moving at point A and moving at point B, and so we call the velocity at A would be VA and the velocity at B would be VB. If there's a change in that velocity, that would correspond to a change in kinetic energy, which is has the same units as work. So therefore, if we're going to have a difference in velocity, then we can say that the work done in changing the kinetic energy from point A to point B is the kinetic energy at B minus the kinetic energy at A. So 1/2 mvb squared minus 1/2 mva squared. Again, we can replace the mass term by 1 since it's a unit mass, and then we can also combine these terms, so we end up with VB squared minus VA squared divided by 2. So that's part 2 of our work. Finally, part 3, the work done in compressing the fluid isothermally. Maybe as you move from point A to point B, we change the volume of the mass. Isothermally means without changing the temperature, so we're not adding any heat or energy through heating it. We're just looking at compressing the fluid. And as you may recall from physics, but work, if the volume is changing due to pressure, and by the way, this is pressure changes. That's what this, why would the fluid compress? It would compress because from going to point A or point B, the pressure might change, all right? And so the work done would be the change in pressure times volume. And when we do that, we have to do differential by parts, as you may recall. So delta PV as a unit is equal to delta P times V plus delta V times P. And now we're going to do a little trick here. As we go to this next line, water is what we call an incompressible fluid. You can put incredible amount of pressure on it and it won't change the volume, only a very tiny amount. So we're going to say delta V is 0. And so the work is then the change in pressure times the volume, which the change in pressure is the pore pressure at B minus the pore pressure at A. And the volume we can define as the mass divided by the density. And again, the mass is equal to 1. It's a unit mass, so we end up with UB minus UA times the density of water. All right, so now we're going to take each of these three components that we just derived and we're going to add them together. Work number one, the work done in lifting the mass, is GZ. Work number two, the work done in changing the kinetic energy, VBA squared minus VB squared minus VA squared over 2. And then the work done in compressing the fluid, or expanding the fluid if you will, UB minus UA over the density of water. And that is called the total potential. Now, to simplify this equation further, we are going to divide everything by gravity, and to get it in terms, the potential in terms of weight rather than mass. So we divide the left side by G and the right side, so G divided by Z simplifies to Z. VBA squared minus VB squared minus VA squared over 2, we end up with a G in the denominator. And then dividing this by gravity, the density times the unit, times gravity is equal to the unit weight. So this converts from density unit to unit weight unit. Again, density is mass per volume and unit weight is force or weight per volume. So we call this is Bernoulli's equation, and it represents the units of this now are in units of length. So Z, the difference in height, obviously is a unit of length. VB squared minus VA squared over 2G, that resolves to length units, and then pressure divided by unit weight, that also resolves to length units. And so we call this this potential divided by gravity, which has units of length, we call this the total head, and it represents the the change in head moving a unit mass from A to B. Now, head is hydraulic head, piezometric head. Again, a really fundamental, important part of groundwater modeling. The best way to think of it is kind of like potential energy, and I'll come back to that. But let's continue on a little bit. And so the change in head from AB is this term we've derived. But let's remember that Z is equal to the distance between the elevation difference between A and B, which is ZB minus ZA. Therefore, a better way to write this is ZB minus ZA plus the velocity term plus the pressure term. And by the way, if you combine all the B terms and then all the A terms, you can end up with ZB plus VB squared over 2G plus UB divided by unit weight of water minus ZA plus VA squared over 2G plus UA over the unit weight of water. So we have two very similar looking terms here. And what do they represent? So this is a form of Bernoulli's equation written not in terms of the difference between 2 points, but in terms of what we call the total head at a particular point. So this could be point A or point B or any other point. There's a property at that point which we call the total head, which is equal to its elevation. Now at this point, this Z doesn't represent a difference in elevation. It's the actual elevation of that point, plus V squared over 2G, the velocity of the point divided by 2 times gravity, plus the pore pressure of the point divided by the unit weight of water. Now each of these 3 terms on the right have a specific name and a specific meaning. Again, taken together, they form the total head, but the elevation Z, we call that the elevation head, and clearly it has units of length. V squared over 2G, we call that the velocity head, and U over gamma water, we call the pressure head. So each of those three things added up represent the total head. And it turns out they each have kind of a specific physical representation. So the elevation head is simply the distance to the point above some arbitrary datum. What do we mean by an arbitrary datum? Well, you just have to establish some uniform basis or datum for measuring that elevation. The most common datum we use is sea level. So we just take the elevation of a point above sea level, and that works. But theoretically, it can be whatever other datum you decide on, as long as you use a consistent reference to that datum among all the different points you look at. So that's real easy. It's just the distance up to the point in question. The velocity head is equal to the velocity of the water at that point divided by 2 times gravity. So the faster the water is moving, the greater head it has. And if it's moving really slow, it has the faster the water is moving, the greater velocity head it has. And the slower it's moving, the lower the velocity head. Now, if you've taken fluid mechanics and you've analyzed the flow of water through a pipe network, for example, you're familiar with velocity head, and it has a very strong impact in those particular cases. But in groundwater problems, we typically are looking at very low velocities. So in this table, I've put together some different velocities in feet per second that might be in the range you'd see in groundwater. Well, groundwater moves very slowly. So if you're looking at 1 times 10 to the minus 6 feet per second, that's very possible, or 10 to the minus 4. Now down at the bottom of that table, I have 1 times 10 to the 0, so that's 1 foot per second. And if you convert that, for those of you watching not used to English units, it'd be about 1/3 of a meter. So if you look at the corresponding velocity head, for 1 times 10 to the minus 6, we get 1.6 times 10 to the minus 14th feet. So that you couldn't even measure that. That's so small. Even when you get down to 1 foot per second, which is for groundwater, that is almost unheard of. The only time you'd see water flowing that fast might be right next to a well that's pumping water out. And even then, it's 1.6 times 10 to the minus 2, so that would be just a couple millimeters. Just pretty much negligible. Therefore, in groundwater problems, we generally neglect velocity head. It's not worth keeping track of. So we're just going to strike that from our equation. And then finally, the pressure head is equal to the pore pressure divided by the unit weight of water. And I'll show you in a minute that has a very simple representation. Therefore, Bernoulli's equation for groundwater systems is very simple. It is Z plus U over gamma water. Or written another way, it's the elevation head plus the pressure head. It also has a very simple physical representation. The total head is the level to which water would rise in a piezometer inserted at the point in question, measured relative to some arbitrary datum, for example, sea level. So a piezometer would be a tube, like a monitoring well. If you put some sort of tube in the soil, and then you look at how high the water rises in the tube, if you look at that water level and measure it relative to your datum, that is the total head. Okay? So it's a really simple physical representation. So let's look at an example. So here we have some saturated soil, and that's shown in orange, and on top of that saturated soil we have some freestanding water shown in blue. And on the right, let's start on the right first. We have point A. This is in the lake, in the water. And we're going to select a datum at the bottom. That could be sea level. It could be whatever. We're using a common datum. So for point A, the elevation head, it says ZA, we could also put HELA, so the elevation head to point A is just the distance from the datum to point A. And then the pressure head represents the height to which water would rise in a piezometer or standpipe above point A, measured from point A. So remember, we kicked off this discussion about the pressure is the height above the point, the height of water above the point in question, times the unit weight of water. Well, the pressure head is simply that height. Okay? So it's really simple. And the total head is just the sum of those two. Okay? So the total head is equal to the pressure head, this distance up to A, plus, the elevation head, the distance from the datum up to A, and then the pressure head, the distance from A up to where the water would rise. Okay, now let's look at point B. Same thing, we're going to use the same datum. The elevation head for B is just the distance up to point B. The pressure head for B is the water level to which water would rise, and assuming this is saturated and hydraulically connected, and there's no flow occurring, it would just rise up to this water level up here. So that's the pressure head at B, and taken together, these two form the total head at point B. Here's the key point. In groundwater systems, water always flows from high head to low head, and it will only flow if you have a head differential. If the heads are the same everywhere, like they are in this example, water does not flow. But if the total head is different as you move through the soil, water is going to flow from high head to low head. And it's not just the pressure, it's not just the elevation, it's the combination of the two, which we call the total head. Okay, let's revisit this in light of our current understanding of Bernoulli's equation and label a few things. As you may recall, we have water above point A at a height of x and water above point B at that same height, and that water is representative of the pore pressure, and it's also a direct representation of the pressure head. So this x here, right B, that would be the pressure head of point A. Reposition that. And then this x down here, the pressure head at point B. Okay, those are already labeled. Now let's look at the elevation head. This distance, right? Whoop, before I do that, I have to define a datum. Let's mark our datum. So we're going to make an arbitrary datum down here. So this would be the elevation head of point B. And then looking over here, this distance would be the elevation head at point A. And now we want to shift our attention. What is the total head? Well, the total head is the sum of the elevation head and the pressure head. But again, a simple way to think of it is if you just take the height to which water would rise above the point in question, measured relative to our datum, this becomes the total head for point A. And over here for point B, we have the height above the datum to which water would rise. We'll call that the total head of point B. Since the total head of A is greater than the total head of B, water is going to flow from point A to point B. Okay, now let's shift to our next example, example 2. And again, let's draw ourselves a datum down here. So let's start with point A over here. So I'm going to draw a line. Let's make that a little bit shorter. Whoops, there we go. Make room for my other lines. And let's draw a line here. Let's put one here and one here. So we have a number of distances. We have these distances. I'm going to mark these and then we're going to label them. And so this would be the elevation head at point A right here. This would be the, here's my label. There we go. This would be the pressure head at point A. And then, let's see, I need one more line over here. This distance from here to here would be the total head of point A. And over here we have the pressure head of point B, the height to which water would rise above point B. And we have the elevation head of point B. And then finally, if you just go from the datum up to the height to which water would rise above point B, we have the pressure head of point B. Again, elevation head, pressure head, total head, elevation head, pressure head, total head. Again, since the total head at point A is greater than the total head of point B, water flows from A to B. And in this case, the pore pressure at A is greater than B. If you look just at the height to which water would rise above the points, there's a higher pore pressure at A than B. The elevations are the same, but total head is a combination of both pressure head and elevation head, and water always flows from high head to low head. So this is a principle that's really important in groundwater modeling and understanding flow in aquifers. The elevation, the total head, another way to think of that is the water table, measured relative to a datum, which is typically sea level. So water is always going to flow from where the water table is high to where the water table is low. That's a really simplistic way of viewing it. And it flows in the direction of the maximum downward gradient. So where there's the steepest drop off of total head or water table elevation, that's where the groundwater is going to flow. The whole point in groundwater modeling is to come up with an estimate of how the total head is distributed throughout an aquifer system, because once we know that, we know how fast the water is going to flow, we know at what quantity of water is going to flow, but it all comes back to this principle of hydraulic head. So now in our class we'll do some exercises associated with this, and then next time we'll build on this and come up with something called Darcy's Law.